So you have the equivalence relation and that induces a partition. Now what one does is that this whole equivalent class of fractions is identified as a single ratio, and that is what you call a rational number. Okay, for instance, this whole block will be identified with 1 by 3 and there are no more common factors to it. Here there is a common factor, so you put them all together. Okay, so you can identify with them something what you call 1 by 3, or you write this whole thing as 1 by the block containing 1 by 2. This may be 1 by 2. Okay, so or something like 17 by 19. If it is here, then the whole block will be denoted. Okay. Now the question that you ask is, so now you see we have a certain complexity here. What is that? It's a collection of all fractions. There is an equivalence relation that we have introduced. Now we have identified some of them together, and it is partitions into this. Can you define what is called, or can you extend the notion of addition, multiplication, and the order structure to this? The answer to this is yes, you can do that. So let me do that. It's the same definition that you use. You say that 1 by or x1 by x2 plus y1 by y2, you define it as what? The class corresponding to this we have already defined. For example, I give an example 1 by 3. The block 1 by 3 plus the block 1 by 2 is equal to the block corresponding to 1 by 6. It's a definition. Okay? But there is a question. Is it well defined? Because the reason is this. After all, I may take 1 by 3 and 1 by 2 to construct, fabricate this 5 by 6. But somebody else might take this as 2 by 6 here and then take this for 3 by or what do you call 4 by 8. And then apply the rule of addition. What do you get? By definition, this will be 48 here, and then you have 16 plus, that's equal to 40 by. So the question is this the same as this block? That's the question. Is this block the same as this block? If you get it, well, then your addition is well defined. Otherwise, it becomes depends on the choice of the representative element. Okay, so we don't want that. So you see that you easily see that the common factor here is what? You have what is the detail? Yes. 8 is a common factor and you get 5 by, if you remove that, then you get 5 by 6. Okay. So this is equivalent to this, this is equivalent to this, implies this is equivalent to this. Okay. Therefore, you see that the addition is well defined. Similarly, you can work with the order structure. We say that x1 by x2, there is no ambiguity in this, y1 by y2, if and only if x1 by 2 is less than x2. Okay. Similarly, so any representative member you can use. Okay, that's the thing. You don't have to see, one person might pick up 2 by 6 to represent this. Another person might take up 27 by 81 to represent this. No matter who takes part, addition is well defined, the order structure is well defined, and also we say that x1 by x2 is equal to y1 by y2 if and only if x1 by x2 is equivalent to y1 by. That's the definition. Okay? That's the definition. Right? So this we have defined earlier. What is the meaning of that? x1 by 2 equal to x2 by 1. Right? So equality is defined, less than is defined, greater than is defined, addition is defined. Now multiplication also you can check this property. Into is well defined. This is defined as the class this is the class, and you can also show that this is well defined. For instance, x1 by x2 is equivalent to x1 prime by x2 prime, y1 by y2 is equivalent to y1 by prime by y2 prime, then x1 y1 divided by x2 y2 is equivalent to x1 prime y1 prime divided by x2 prime y2. Let's see, that's what you have about the rational numbers. So these are the rational numbers that you have. So this whole system of blocks now constitute what is called the rational numbers. Now I can give another geometric interpretation of that, but let me not, well, maybe since I am permitted to go ahead with it, let me go ahead. Then what you have is this. See, what is this n cross n? N consists of 1, 2, 3, let me mark this like this. 1, 2, 3, 4, and then this I have 2, 3, 4. So what are the points in n cross n? They are nothing but the lattice points. The lattice points are these junctions of these lines that you have. So you have this one, this is 1, 1, this is 2, 1, 1, 2, sorry, 2, 1, 1, 2, 1, 3, 1, 4, etc., etc. These are the points which turn out to be this. Now let me see how these fractions, each one is identified with a fraction. Okay? But which rational number it is identified? Okay? Okay. So this is, if you take this one, this one, this one, this one, what are these numbers? This is 1, 1, this is 2, 2, this is 3, 3, this is 4, 4, etc. They form a block. Okay. Now join this. See, this is 1, 2. Okay. 1, 2 with 2, 4. Okay. So you join this. So this line passes through these vanishing lines. And so on. Similarly, if you take this, then this is going to go through these points. So each of these radial lines that pass through this ordered pair of points corresponds to a fraction, and that fraction has to do with the tangent of the line, or the tan of this line, or the cotangent of this line. You can the angle properly chosen. Okay. So they are the equivalence classes as you see here. Okay, this is a more Venn diagram type thing. This is a more concrete picture of this. So each one corresponds to a rational number. Okay. What are the main important change that has taken place? And this is what you have. If you start with natural numbers, now you see that there is a number next to a given natural number. Okay? Because every number other than 1 has both a successor and a predecessor. They are just lying next to it, in the sense that in between, you say that x and y are lying next to it. What does it mean? It means that in between x and y there is no other natural number. So the concept of nextness is there in. Do you have a similar concept here? Given a rational number, can you find a rational number next to it? What would this mean? This means that if there is a rational number here, say called P, and there is another rational number here, Q. Now, if Q lies next to P, there should be no rational number between P and Q. Okay, but that is not the case. Given two rational numbers, you always know that P plus Q by 2 lies between. You can prove this. There is a rational number in between, and this is by definition a rational number. Okay. Right? So there is no concept of nextness any more valid in what you call Q, or the class of rational numbers. So no concept of nextness. So this is the biggest casualty. No nextness. That means, given Q, then you have the three, one of the three things happening, that is either P equal to Q, or P is less than Q, or Q is less than P. Okay? Right? So if P is less than Q, there exists another R belonging to Q such that P less than R less than Q. So there exists a rational number lying between P and Q. Once again this applies. So there are infinitely many rational numbers lying between two unequal rational numbers. So this is one property that is markedly different from what you see on the natural numbers. So natural numbers have a discrete structure. But here, you don't have that discrete structure. The concept of nextness is the causality. It is completely gone now. But all the other properties do extend. You can extend addition, you can extend order relation, you can extend what is called the multiplication. But you don't have any more the concept of nextness. So we are working with the rational, I should say Q plus, because we are working with Q plus only right now. We are not going into Q minus or anything. Right. So let me go to the, let me just put this down and in the following format. So this is it. Then you have addition, multiplication. Three properties are there. Nextness is there. Is there? These with the usual properties. Now you have extended this. You have extended this to Q plus. You have extended this to Q plus. What do you have? You have extended addition. You have extended less than. You have extended. One more thing I want to say is that, every natural number can be discovered as an element of Q plus. How do you do that? So if you take a natural number n belonging to n, then n by 1. This class is in Q plus. And this can be identified, n by 1, the block corresponding to n by 1 can be identified with n. Therefore, every natural number is embedded in what I call Q plus. So that is the structure that you have. Q plus addition is an extension of the addition here. Less than is an extension of the less than here. And multiplication is an extension of the multiplication here. This is clear because if you conceive m by n, m belonging to n, n belonging to n, then this is identified with m by 1 and this is identified with n by 1, and m by 1 plus n by 1 is identified with 1, and this is identified with m plus n. Okay, so addition is properly identified. So also you can show that is less than, greater than or equal to, all these can be identified. And so also multiplication, because m by 1 so m is identified with the block m by 1, n is identified with the block n by 1, mn is identified with the block mn by 1. So you see multiplication also is an extension of the concept of addition or multiplication on n. Okay, but with one causality, namely the nextness is lost. Once again, let us ask a few more questions. Like, Suppose you have x1 by x2, y1 by y2, then you can actually show that there exists u1 by u2 such that x1 by x2 plus or more than 3, you can do this. Okay? Right? If this is so. So given x1 by x2 the block, y1 by y2, three things are possible. Either this block is equal to or greater than one of the three things can. Count all the three. Okay? Accordingly, you can write down the conditions. So it is not that in all cases you can find u1 by only if this condition is satisfied, this is true. Okay? Otherwise, what happens is that if y1 by y2 is less than x1 by x2, and you have a v1 by v2 such that y1 by y2 block plus the block of v1 by v2 equal to the block of x1 by x2. Now let us look at this one. Suppose there is x1 by x2 and y1 by y2. You ask the following question: do you have a rational number p such that this is a question that you are asking. Does there exist? The answer to this is yes. Always there exists a p, which is of the sum u1 by. Okay. So what will be the u1 by u2 that you have? u1 by u2 will have to be having the property that x1 by x2 is equivalent to y1 by y2. Or you should have u1 by u2 you can manufacture as y1 x2 by y2 x1. You choose this, then you have this property. So P will be equivalent to u1 by u2. Okay? Right? So this equation always has a solution. This equation has always a solution. So at least in the case of positive rational numbers, the equation P into psi equal to Q has a unique solution. Whereas P plus psi equal to Q has a solution only conditionally. Still we have not achieved got the question, got this question solved. So our system is not big enough to solve this question for all P and Q. Okay? Whereas As regards to multiplication, yes, it is there. Okay, so this is the position you have. Now, one of the things that we normally do is try to put them on a line. Okay. Try to put them on a line. Okay. So you start marking 1 here, 2 here, 3 here, etc. N here, n plus 1 here. Now they form what is called the number system. Okay. Now what you do? What is that you are doing? You are introducing things like m by n and all that speed. So these are new entities that come in and start filling the place. So somewhere here I will put a barrier here, not marked yet. So you see that now you see all these points, not all, but many of these points have a number. When they are all placed here, it goes even less than 1, it goes greater than 1. But you see that a few things happen. You remember on n we proved that every subset has a lowest element. In n, if you take any subset, it has a minimum in that set. In Q, if you take, there is no minimal element. For instance, in n, if you take the whole of n, what is the lowest element? The smallest element that you have is 1, according to the order structure. But suppose you take q plus n. What is the smallest element? There does not exist a smallest element in 2 plus. Why? Because suppose there is a smallest element, then this is of the form x1 by x2. Now you look at this one, x1 by 2x2. x1 by 2x2 is always less than x1 by x2. So if this were the smallest element, then you have something still less than that in that set. Okay? So there does not exist a smallest element in Q plus, whereas in n there exists a smallest element in V. That's one special feature that you have. So we have the following properties now. Every natural number has a unique natural number next to it to its right. Every natural number other than 1 has a natural number to its right and to its left. What you call the successor and the predecessor. Now there is a concept of nextness in n. This is essentially a discrete structure. So n has a discrete structure. Given any non-empty subset of n, there exists a unique smallest number. N has no largest number because if n is there, n plus 1 is there. Further, the equations a plus x equal to b has a solution sometimes and not for all choice of a and b, this equation has a solution. Similarly, the equation ax equal to b does not necessarily have a solution. Sometimes it has to be. For instance, if you take A equal to 3 and B equal to 6, then there exists a natural number 2 such that 3 into 2 equal to 6. So sometimes it has a solution, but it doesn't have. But when you come to rationals, you see that every natural number is a rational number. So that is what I said. N is embedded in Q plus. Okay. Then the concept of nextness wither away. You don't have any more the concept of nextness. Now this is really frightening in some way, because a word we are used to is something where you have the concept of nextness. You are familiar with. Okay. What is to your day-to-day experience? The nextness is there. You don't feel the absence of that. Okay. But now you are running into a world of fantasy through fractions, or what you call the rational numbers. So the rational numbers Q plus that you have defined does not have the concept of nextness. This is something which you cannot immediately conceive with your day-to-day or reconcile with your day-to-day experience. Now this is something very interesting. Now you have also the equation P plus X equal to Q, given P and Q, need not have a solution. So that problem has not been solved at all. But when it comes to the following equation, namely Px equal to Q, this problem has been solved. It is given P and Q in Q plus, there exists a rational number x such that, or u such that Pu is equal to Q. So this equation always has a solution. So that's a bit of a solace. So we have extended this and got one irritant out of our way. Okay. It says that our extension is still not completely satisfactory, but it is satisfactory to some extent. That is, partially it has achieved the existence of the solution of the A equation, not fully the linear equation that we have. The linear equation will be something like Ax plus b equal to c. Given A, B, C, does it have a solution? Okay. We cannot say this. But if your equation is something like Ax equal to b, where A and B are both positive rationals, then it has always a solution. So partially it has been met. Okay. So this is the position that you have. Now I think I stop this talk at the moment here, and certainly I will continue with it to take it to the next level soon. That is, extend the rationals to the reals, and that has been our objective. I have not completed it, but this will be available in my YouTube channel in a day or two. So those who have seen this can always log on to that part and enjoy it. So thank you very much. At this stage, I will return with the real life. Thank you.